Mute. 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 So, welcome everyone to this morning session on visual analytics for problem solving. And my name is Jan Kohlhammer, and I will be the session chair for this session. We have 4 papers who all address different topics within problem solving application and domains. And we will start with the first paper by Xuan Li and colleagues on warehouse with a visual analytics approach to facilitating warehouse location selection for business district. And we will hear his presentation now.
Hi everyone, welcome to my talk. I'm going to present my Eurovis work, Warehouse with a visual analytics approach to Hi everyone, welcome to my talk. I'm going to present my Eurovis work, Warehouse with a visual analytics approach to facilitating warehouse location selection for business districts. I'm Chuan from WeBank China. This is a joint work with HKUST. Selecting a proper warehouse location serving to satisfy the demands of the goods from a center business area is important to a successful retail business. For example, we should consider factors like distance from the warehouse to the business districts. The retail price should not be too high, and the size and the layout should be reasonable. For example, I want to find an ideal warehouse with good warehouse qualification, regional functionality, good traffic conditions, and lower renting cost, etc. To tackle the problem of warehouse location selection, we need to adjust the following challenges. The first is the large solution space. Organized relevant heterogeneous data is very expensive, especially due to limited budget and constraints of human resources. Failure to make sense of the valuable information may cause different events, even bad warehouse selection. Second, uncertain traffic conditions. As we mentioned that location is very important, but only consider the distance is not enough without considering the traffic conditions. Third is varying business preference. Different retail business may have different requirements for their preference. This figure shows the system architecture and interaction pipeline, which consists of the back-end engine and the front-end visualization. The dataset we use recalls four types of information. Urban network data comprise a direct graph of the city. GPS trajectory data includes the trajectory snapshots of the chunk status. Warehouse data include the attributes of the warehouses, and the business store data consists of the basic properties of the local business stores. To evaluate the traffic conditions from a selected warehouse to a business district, we first use load network matching algorithm and divide the trunk trajectories to map the road network. Then we divide the whole day into 48 time slices and count the traveling time on each half-an-hour road segments. To handle the missing data of some road segment, we leverage a mixture factorization to calculate the traveling time on the missing segments and calculate the path with the shortest time duration from one place to another, starting at a specific time step. In this paper, we consider 6 factors in the back-end engine: unit price, stock holding capacity, average distance to shops, average distance to main suppliers, number of nearby main suppliers, and number of nearby freeway entrances. We weight these metrics by CMOS procedure and rank the candidate warehouse by TOPSIS. Details can be found in our paper. The warehouse inspection view consists of 4 parts: an interactive view for users to field business districts or markets to avoid visual clutter. B and C show the distribution of business districts or markets, and D shows the cumulative congestion coefficients over distance for the selected warehouse. The warehouse comparison view allows users to investigate the differences among a few candidates. 3 axes indicate the delivery distance to the business district, and 3 departure time steps from the warehouse, and the 4th one means the delivery distance to the market. The height of the curve represents the normalized delivery time from the warehouse to the business districts or the markets, with the solid lines indicating the median value of the traveling duration on the corresponding axis. We introduced a real case conducted by E2. He first selected the region in Jiading District, Shanghai. The system automatically retrieves the candidate warehouses from the pool within 40 kilometers away from each business district. To evaluate the recommendation results, we compare the value distribution of the 3 metrics of the set of recommended warehouses and the rest. From the 3 group of box plots, we find that the value distribution of all metrics from the recommended warehouses is generally more stable than the other set, indicating that reliability of the back-end recommendation algorithm. After systems recommendation and ranking, E2 filled out 5 candidates for further inspection. The second one is close to the business district, but far away from the markets, while the opposite is true for the first warehouse. From the warehouse comparison view, he could witness that the warehouse indicated by the orange color has a better performance at 6 a.m., 6:30 a.m., and 7 a.m. departure time steps. The warehouse distribution also indicates that orange warehouse takes less time and shorter distance to the business district. From the ranking view, the expert found that the second warehouse is more expensive than the first one. However, the distance in the price is small, while the delivery time of the second warehouse is much shorter. Therefore, he tends to choose the second warehouse. However, he finds that the second and the fourth warehouse are similar, and he just compares them. He identifies that almost every aspect of the 2 warehouses are similar, and he turned to the ranking view for more details. He found that although the area of the fourth warehouse is less than the second one, the price is much cheaper, which also meets his requirements. He then changed his mind and chose the fourth one as the best candidate. We use a video to demonstrate the process of the case study. We invited 18 participants from the company and compared our system with two alternative systems. One is original dish system as a baseline. One is a preliminary system. We counterbalance the three systems and conduct the two tasks. The first task is to observe the relevant information of a center category warehouse, and the second task is to evaluate the traffic conditions for the selected warehouse. We compare four aspects of the system in terms of informative decision making, visual design, and system usability. Details can be found in our paper. Warehouse with use familiar visual metaphor and conduct a user-centric process. After introducing the system, users can develop a customized path for exploration. Our system has a good generalizability in terms of design and algorithm. Regarding the scalability, we can control the size of the user-specific business districts so that the system would not be overloaded by a large number of business districts. Also, we find the preliminary version is a good start for the experts to get familiar with our system, and we can also take the chance to test the initial designs. To conclude our work, we propose a visual analytics system to support an analysis of recommended candidate warehouse and a novel visual design to facilitate users in inspecting and comparing multiple candidates at the same time. In the future, we will consider the special character of different warehouses as a case in which multiple warehouses are a better solution than a single one. So, that's all. Thank you for your time and wish everyone safe and health.
Okay, thank you very much for this interesting presentation. So we have time for a few questions. As you know by now, probably, you can post your questions both on the Discord channel and on YouTube. And I will see your comments and questions and will read them out loud so that Xuanli can answer to those. While you are thinking about your first question, I have one myself. In your evaluation, you show that you compare the final system to a preliminary version and a GIS system. Can you say a little bit more about these comparison candidates?
Yeah, actually, we seldom find any existing system regarding the warehouse selection problem. So at the initial stage, we built a preliminary version to make sure that our target user are familiar with our approach, because we compile the backend model with a visualization interface. So they have to understand the output of the model, so they can familiar with something they are not sure, and they can leverage their domain knowledge and to confirm the efficiency of the system. So later on, we find that if some views are not preferred by the target users, so we abandon them and keep some of them. So we also take this chance to verify that where the visual design are appropriate. So actually, there are two experts for the system for our approach to build two versions of systems. Yeah.
Okay, and the GIS system is more the system that they worked with before you introduced the new system. Is that correct?
You mean that the deployment, right?
In the evaluation, you compare your system also to a GIS system. That's the system that they had in their company before. Okay. So, okay. Maybe one other question. Right now you're looking at one warehouse to be selected, or one warehouse location. Did you also think about a network of warehouses where some of these
Yes.
have several of these warehouses and they
Yeah,
don't
yeah.
close to each other? And did you also take this into account?
Yeah, in some cases, it's better to select two warehouses than one single warehouse, because due to different conditions and due to different traffic conditions. So this should be the future work. That currently we only consider one warehouse as a solution, but in some cases they are not better than if we simultaneously take two as a whole package of solution. Yeah, we have mentioned this in the limitation.
Oh, sorry. There's one question from Kevin Elaine here. Do you think other data sources can be added to the system to take into account the context, further context?
Excuse me, can you repeat it? Question?
Oh, sorry. So the question is, do you think other data sources can be added to the system to take into account a further context? So how open is your system to additional data sources?
Actually, all the data are public data sets, and so some of the data, like the warehouse locations, the business districts, are from the public data set and from the some websites, and the network and also the traffic are collected from the GPS devices. In the future, some more data can be also adapted, like some data from the real business scenarios, because this is the initial attempt to solve this problem. But during the deployment, we also met some real world problems, like the feedback. Yeah, where the selected warehouse is there can meet their real world requirements. This will take some time to verify the efficiency of the final selected one. Yes, actually there are two versions of the system, and for we compare how the target users can understand the functions of the system, and the system has been deployed in a real company, retail company, from collaborate with WeBank and with think that they can serve they can save much time and energy, because originally they just collect multiple data from offline, and is very labor intensive. So I think the recommended warehouses can can be their top solutions, and they can continue to verify them offline.
Okay. But one last question. Were the participants in the study from the same special domain with similar preconditions?
The participate, sorry, can you repeat it again? Yeah.
So the question is, if the participants in the study, were they from the same special domain? I think they were all from the company, you said, right? The study participants.
Yeah, the participants are from our collaborated company, the retail company. Some of them are responsible for selecting houses, and some of them are the one who check the routes or check the condition of the warehouses. So they all have the experiences of selecting warehouses in their business requirement. So we choose them because they knew the requirement, and knew what a good warehouse will bring what kind of benefits a good warehouse can bring to them. Yes.
Okay. Well, thank you very much. Thank you for the questions also. If you have any more questions, there's also the Discord where you can post your questions, and only will see that.
Thank you. See you later.
Thank you very much. We come to our second talk, given by Calvin Lee, on resolving conflicting insights in asynchronous and remote collaborative visual analytics.
Hi everyone, welcome to my talk. I'm going to present my Eurovis work, Warehouse Viz.
Hi, I'm Calvin Lee. Today I'm going to present our research work for resolving conflicting insights in asynchronous collaborative visual analysis. Collaborative visual analytics allows a team of analysts to explore data together by using shared visualizations. Many research works have been contributed to collaborative visual analytics. However, method for identifying and resolving conflicts in the collaborative analysis results is missing. In real-world applications, Data explorations are often interrupted by conflicting insights from different analysts. So methods for identifying and resolving conflicts are crucial for obtaining accurate results for decision making. This is especially important for asynchronous collaborations, because the analysts cannot directly communicate with each other. To address this problem, the goal of our project is to take the initial step for providing conflict resolution in collaborative data analysis and visualization. In our approach, we use insight graph for managing the findings and insight extracted from visualizations. And we use declarative language for representing all the visualization. And we use the Git revision control system for managing the collaboration process. Insight graphs. Users can create nodes to represent insights and links to represent the relationships between insights. Visualizations can be attached to any nodes and links as insight provenance. For declarative languages, first, they are flexible for data exploration by rapidly specifying various visualization charts, and they are easy for understanding and tracking insight provenance, as it can tell us how data are transformed and encoded in the visualizations. More importantly, it allows visualization to be stored as texts and files, which can be effectively used with the Git revision control system for tracking and managing the shared results, as well as detecting conflicts. Here's our system framework. There are 3 modules. The exploratory data analysis module is for users to create visualizations using declarative language. The findings and insights can be externalized and arranged in the Insight Management module, which uses the insight graph and a set of visual interface for managing analysis results. Changes to the shared results are managed by the Collaboration Management module, which leverage the Git revision control system for detecting conflicts and combining results. Based on this system framework, we developed a prototype system, which we named COVA. Here's the primary user interface. The left side panel is for data exploration. Users can input declarative specification for creating visualization charts. By default, COVA uses the P4 declarative language, but it can be configured to use other languages, such as the Vega or Vega Lite. The visualization and the associated insight can be externalized and arranged in the insight graph, as shown on the white panel here. For collaborative data analysis, the findings in the insight graph can be shared and combined with other results using the Git revision control system to commit, push, or pull the result to or from a shared repository. COVA automatically checks all the changes to each insight graph and provide a visual interface for browsing the revision history. For identifying and resolving conflicts, 3 common types of conflicts are currently supported. The first type is property mismatch, which occurs when 2 users edit the same node or link in the insight graph. For example, user A may label a node to be important, while user B may label it to be not important. The second type of conflicts is node dissonance, which occurs when a user edits or adds links to a node that has been already deleted by another user. The third type is provenance mismatch, which occurs when different users attach different visualization or annotations to the same node or link. Here's COVA's visual interface for identification and resolution of conflicts. It shows the 2 insight graphs from 2 different analysts that have conflicts. On the left panel, it lists all the detected conflicts and allows users to choose how to resolve each conflict by using their own results from the other analysts, or merging them by using both the looks and links in the 2 graphs. Based on the choices of the users, the results are combined and displayed on the right panel. Alright, here's a quick demo of the COVA system. Users can create different charts to explore the data and record the findings in insight graph. The results can be committed at any time and shared by pushing it to the Git repository. Visualization can be attached to any nodes and links as insight province. And user can enter any annotations as well. When there are new results shared by other users, they can be pulled from the server and merged with the current user's results. If there are conflicts in the results, the visual interface for resolving conflicts comes in and allows the user to choose how to merge the two insight graphs. After solving the conflicts and combining the results, users can continue to explore the dataset and commit more findings. Okay, that's the demo. For evaluation, we compare our prototype system COVA to a baseline version. In COVA, we used our visual interface for identifying and resolving conflicts. In the baseline system, we used the conventional graph merging method to combine the results. That is, nodes and links with the same labels will be merged, and different labels will create different nodes and links in the combined graph, even they are referring to the same insight. And users have to manually edit the graph to fix the results. We conducted a user study with 16 participants, and they are assigned to either the COVA or baseline group, with 8 people in each group. The user study has 4 stages. The training stage provides tutorial for using the systems. The test stage requires the participant to perform specific tests to explore a dataset. In the free-form stage, participants are asked to continue to explore the same dataset and commit more findings. At last, the review stage asks questions for rating the system. For a controlled user study, we simulated an asynchronous collaboration scenario in which each participant is working in a team with a simulated collaborator. In the test stage, each participant starts with an initial insight graph and is required to explore 3 specific aspects in a dataset. After each participant commits the first set of results, the simulated collaborator will push additional results to the repository. So the participant has to combine all the results before pushing it to the server. After the test stage is completed, participants are asked to continue explore the dataset and add more findings to the combined results. They have 10 minutes, and they can explore any aspects or whatever they want in the dataset. Based on the answers from all the participants to the questionnaire in the review stage, COVA received a significantly higher rating than the baseline for the test of understanding the insights saved by the collaborator. This shows that COVA's method and visual interface can effectively help users to better understand the results in collaborative data analysis. Additional to understanding the results, we also analyzed the final insight graph from all the participants in the free-form stage. And we found that COVA allows significantly more insights to be generated using the combined results. Both the number of nodes and links in the final graph are higher in COVA than the baseline. If we only count the nodes and links that are connected to the nodes that are added by the simulated collaborator, on average, the number of these nodes are higher in COVA than the baseline, but the effect is not significant. But for the number of these links, it's significantly higher in COVA than the baselines. This means that participants have added more new findings that are connected to the results that are shared by the collaborator, which indicates a better collaboration. Alright, before concluding these talks, I want to point out several limitations. While our system is a prototype for conducting user studies, future system design should provide better user interface for data exploration. Instead of directly using declarative visualization language, it could use graphical user interface for creating charts and automatically convert the charts to declarative language. So the user does not need to write declarative language, but we still can use it with Git version control for managing conflicts. Also, It needs to provide a better way for externalizing insights and adding provenance. For our user study, it's limited to only 2 analysts in collaboration. In future work, we plan to conduct user study with more users in collaborations. Nonetheless, our method and result have shown that supporting identifying and resolving conflicts can provide a better collaborative visual analytics system, as it can allow better understanding of the shared analysis results and lead to more finding and insights in collaborative data analysis. We believe there are a lot of opportunity for future research in this direction for advancing collaborative visualization and visual analytics. And thank you very much for listening to this talk.
Okay, so thank you very much for this interesting presentation on insights and conflicts. And we already have one question from the audience, from Kevin. And he asks, what sort of insights participants are asked to find, and if you can elaborate a bit on that.
So this is actually a data set about global terrorist attack. So the participant were asked to find insight about how different terrorist group make attack on different region of the world, or how many attack they make each year. It could be something like which group of terrorists actually make the most attack, or has the attack is causing the highest number of wounds and number of kills in those attacks. So they can represent those insight using bar charts, line charts, and then they can arrange those charts into an insight graph as a log and lengths. So those are the insight and the relationship between the insight, which is presented in a log length diagram, like a graph representation of that. Yeah.
Okay. I had a first question also going a bit in the same direction. The participants in your study, they were not experts in the topic of terrorism. They were looking at this information as a quite fresh information for them. Did you also see, if you compare expert insights to novice insights, is that also something that you went into, or is that something for future work?
Yeah, the participants are actually not familiar with the data sets, so they're kind of this kind of fresh information to them. So yeah, we did not consider comparing the different level of expertise in the data analysis or familiarity with the data set. So this is definitely something for us to consider in the future. When we decide better or a user study that involve more participant or more user in a collaboration, we definitely want to consider that. Perhaps in a real collaboration, the user may have, the analysts in collaboration may have different level of expertise. Some analysts may have, the lead analyst may have expertise in this topic or familiar with the data set, but the other analysts in collaboration may not be that familiar with the data set. We have different background, different knowledge domain. So that's something we should consider for future study. And how do we consider this into provide a better system for supporting collaborative visualization and collaborative data analysis? Yeah, that's a very good direction for future work, we believe. Yeah.
Okay, thank you. I was also wondering if when I work with the system, in one example, you showed that one participant had to actively say that this is not interesting. So is that what is your experience with that? I mean, when I work with the system, I can say, okay, this is interesting. That's something I'm ready to do. But to label things not interesting, is that something that is a border or a hurdle for people to do?
Well, actually,
Hello,
in that
everyone.
example, I
My
just
name-
try to provide example how a conflict can occur. But in our study and based on our observation, like people tend to not like they will label differently. They might label a particular chart has different have some kind of insight, but the other analysts might label that have a different type of insight, or the insight is actually different. But they actually don't we haven't observed that like people will actually mark down something they don't think is interest. So yeah, I hope that answered your question. That was just I think example, a dummy example for showing how the insight can occur, but it's not actually the actual case.
Okay, I don't see any more questions on the channel. If you have more questions that didn't come to your mind quickly enough, post it on the channel, and we are here all week. Again, Kelvin will take the chance to answer them.
Yeah. Thank you.
Thank you for your presentation and the answers. So this brings us to our third paper now, given by Mong Shuai and colleagues, on sequence dynamics, visual analytics for evaluating online problem-solving dynamics, and we look forward to your presentation.
Hello, everyone. My name is Meng, and I come from the Hong Kong University of Science and Technology. Here, I present our work, SIG Dynamics, Visual Analytics for Evaluating Online Problem-Solving Dynamics. In the scenarios of elite selection in university or interview in IT company, we usually need to select top candidates from a large amount of applicants. During the process, we consider not only their cognitive skills, such as the ability to think, read, learn, etc. More non-cognitive traits have been considered by interviewers nowadays. For example, the motivation, perseverance, self-regulation, and so on. Existing evaluation usually contains one exam or technical interview. However, some skills and traits can only be reflected by candidates' performance and behavior during a long period. For example, the ability to learn, self-regulation. Fortunately, more and more platforms have logged the behavior data, which can be utilized to evaluate a candidate's comprehensive skills. For example, some online problem-solving platforms, Khan Academy, Coursera, NeetCode, they record students' practice history on different programming exercises and math problems. We call the process and progress of solving a series of problems over time as the problem-solving dynamics. We can derive a learner's cognitive skill, such as a learning curve, from changes in the difficulty level of problem solved, or determine the non-cognitive traits such as self-regulation patterns based on the problem-solving frequency. Then, in the elite selection in university or interview in IT company, we can better select candidates by evaluating their problem-solving dynamics. However, evaluating such data is challenging. First, each learner's problem-solving dynamics is multidimensional time series data, and it's difficult to represent such data with meaningful semantics to reflect both cognitive and non-cognitive traits. Second, the evaluation process usually involves the comparison among numerous problem-solving sequences. Third, there is no standard definition of good problem-solving behavior. Different instructors have their own understanding and criteria. Thus, we present SIG Dynamics, an interactive visual analytics system for instructors and interviewers to inspect and evaluate multidimensional, time-dependent problem-solving sequences comprehensively. We derive the following requirements based on the interviews with domain experts. Show a clear overview of overall students' problem-solving performance. Understand problem-solving dynamics from different perspectives over time. Compare or combine the problem-solving performance at different skills. Here we add combine since suggested by experts. They hope to see the collaboration results of different candidates since in the university or company, they sometimes require the teamwork. Last, support an interactive and customized exploration of the evaluation. This is a system overview. It contains 4 modules. The data connection module first crawls raw data. The analysis module calculates problem-solving attributes from both cognitive and non-cognitive perspectives. The visualization module utilizes multiple coordinated views to support interpretation and comparison. The interaction module provides responsive feedback to facilitate exploration. Here is the user interface. The ranking view displays an overall distribution of learner scores and performance ranking in an ascending order. The rank is calculated using one popular ranking algorithm, ELO, based on their performance. That is the incorrect or correct attempt towards each problem. Each line represents a candidate. The distance between 2 lines represents their score difference. The ranking view serves as an overview, and users can select a subset of candidates. The subset selected are plotted on the projection view. Each learner is encoded by a novel glyph, summarizing a person's 6 synoptic attributes: the number of problems solved, the ratio of hard problems, the variety of problem type, the number of submissions, the time studying to try hard problems, and the ratio of active days. These glyphs are projected onto a 2-dimensional space. The y-axis is the ELO rank. The x-axis is a customized rank. The reason is that different users have different criteria, and we allow users to set their weights on different problem-solving attributes and get the customized rank. The weights can be set in the correlation view, and this view also shows the correlation between 6 problem-solving attributes with the ELO rank. The larger the inner square, the higher the correlation. The evolution view expands the problem-solving sequences of a smaller subset of selected learners with time series evolution. It uses a bilateral stacked graph to show monthly problem-solving behaviors, and a heat map-like view to show daily submissions. The comparison view is based on the addition or subtraction of 2 sequences in the evolution view, and demonstrates the contrast and complementariness of 2 learners. Here, we demonstrate our system by 3 usage scenarios. Init analysis and selection. One usage of the system is selecting best learners for training according to their problem-solving history. To select 3 best candidates, the instructor loads all 1,000 candidates from the pool and queries the top 20 calculated by the ELO. Through the correlation view, he found that the number of problems solved, the number of submissions, and the variety of questions answered are positively related to the ranking. He therefore adds the weights of 3 features to get a customized rank. By enlarging the top right corner, he selects the upmost 3 individuals 1, 2, 3, who are top in ELO rank, and the rightmost 3, 6, 9, 17, who are top in his customized rank. By seeing the 6 glyphs, he sees 9 has a much bigger size than others, representing 9 has tried and solved more questions. Therefore, 9 is selected. 3's glyph has a light color, implying less variety questions solved. Thus, he deletes 3 and inserts the rest of the potential contestants into the evolution view. Then he finds 6 has a higher volume of unfinished questions and deletes 6. Seeing the downstream of bilateral stack graph, 2 has no red branch while 1 has a bigger red branch, implying that 2 solved questions with a higher passing rate. Thus, 2 is selected. By comparing 1 and 17, 17 started trying hard problems much later than 1 and seems less willing to take challenges. Thus, 17 is eliminated. Now, 3 satisfying candidates 1 to 9 are therefore selected. Case 2. Personal analysis and training. The second application of psychodynamics is to provide a personal analysis and training. Take individual rank 20 as an example. According to his submission detail panel, the instructor observes that 20 always tried the same problems in several days, but still left some questions unsolved after a few tries. Based on this clue, he thinks 20 was willing to attempt questions, but lacked the perseverance to work them all through. He suggests 20 to ask for help when encountering difficulties and to record the unsolved problems and return to them until solves them. Case 3. Team formation. The third type of application SIG dynamics focus on is to provide insights on forming a team. The instructor can select individuals into the cooperation view and check the addition result of problem types in the collaborative hexagon. For example, a student ranked 5 wants to find a teammate. Here are the collaboration hexagons of 5 with 8, 9, 10, and 11. Based on this, 11 is selected as a teammate since they together form an almost perfect hexagon. We confirmed the 3 usage scenarios with domain experts and also conducted semi-structured interviews with 5 domain experts, 3 coaches of competitive programming teams, and 2 instructors teaching programming courses. Overall, all 5 experts commented that SIG dynamics was useful and easy to use. Our framework and visual designs could easily be extended to analyze series of activities, especially in areas that involve competitions. For example, esports, sports, board games, card games, etc. For example, here shows the competition records of the esports game. We can easily replace the data in our existing system, time, student ID, problem ID results, with the competition result in the esports, like time, player ID, match ID results. And then our system can be used to select the best candidate for the competition. Here are the take-home messages. We presented an interactive system that evaluates learners' problem-solving dynamics from levels of detail, and we introduced a set of visual designs to facilitate the understanding and comparison of problem-solving sequences. We also show that SIG dynamics enhances the evaluation process with 3 usage scenarios and 5 expert interviews. Thank you very much, and I would like to take any of your questions.
Okay, thank you so much for this great video. We are open for questions. I have one to start with. I like your visualization and the dashboard. What I didn't understand was when the pie charts that you show. There's this sector in the pie charts that shows the difficult questions, and for some of these pie charts, it is like tilted to the top, and for most of them, it is the pie chart is to the right. What's the orientation of the pie chart? What's the reason for this?
Oh, okay. The orientation of the pie chart encodes the time students start to trying hard problems. So if it's so in the middle, it means that they start to try hard problems earlier. If it starts in a larger angle, that means they start to try the problems in a later time. Yes.
Okay. So it's about from the time that they started any of the problems to where they started the hard problem.
Yeah. Yes.
And another question also regarding the additional applications that this might be applied for. Which prerequisites do you have for the data that is used? Can you just plug in any data source where you have a ranking of different students, or do you have some conditions?
Okay. I think there is no ranking is needed. We only our system can apply to the scenarios like you have the competition data or competition records, but our system embedded the ELO ranking calculation algorithm. You only provide the competition record. For example, you play a game, then you have your lose or win, those types of competition, and we can compute each players rank automatically. And yes.
Okay. So no, so you can any rating would be fine. So you can apply this to any data set where there's a rating for certain performance.
Oh yes, and yeah, then we can derive those six attributes related with the players or learners or the users' behaviors, and then you can better compare those attributes in a dynamic way because it involves the time information. So yeah, that's it.
And the time is also an interesting topic. Right now, the time that you consider for the performances is stretched over across several weeks, I guess.
Yeah. Yes.
And you also go for much finer grained time.
Yes.
Where you have, for example, performances within 1 minute, or even medical data where you have certain things within a second or so.
Yeah. Yeah. I think time is actually the interesting topic and a little it's complicated problems to deal with. It's difficult to model the time information in the sequence. And yeah, so in this work, actually we summarize the time information for different levels. For example, in the glyph, as you asked, we use time to start solving difficult. We only show some significant features or major features of those learners that involves time information. And then for the detailed things, we leave it into the fine-grained level. And at that time, you already narrowed down to several candidates, and it's easier to compare. Yeah.
Well, thank you. Those were my questions I have. I don't see any further questions online right now. But as I said, this should be an ongoing conference, and if there's any questions on these papers, please feel free to use Discord for that. So, thank you very much again, and
Okay.
come to our fourth paper now. And this paper is called CVIS, a smart emergency evacuation plan visualization system with data-driven shot design. And it's given by Xuan Li. Again, you know him from the first paper, and great to have you for a second round.
Hi everyone, welcome to my talk. CVIS, a smart emergency evacuation plan visualization system with data-driven shot design. I'm Chen from WeBank, and this is a collaborated work with Tsinghua University, Peking University, and the University of Tokyo. I will give you a little bit about the research background. As we all know that tracking human mobility dynamics in a large-scale earthquake evacuation is important. However, due to the large urban data with heterogeneous spatial temporal and multivalent attributes, understanding the evacuation behaviors remains limited. Experts usually use general-purpose visualization software like ParaView or AVS to help them analyze the earthquake evacuation data. However, there are three major challenges. First, experts often encounter massive information, including surrounding environment, damages, and large-scale human movements that need to be visualized. However, due to the limited screen space, only a small part of the information is available to users. In other words, identifying the most notable features behind such massive information is quite important. Second, a feature in the data may fuse and evolve. Planning a way to check the feature dynamics is also a challenge. Third, conventional visualizations often ignore the correlations between features and other attributes. Therefore, it is hard for the users to identify the factors that may hidden a smooth evacuation. So in this work, we propose a novel visualization system, CVIS. The system contains of three parts. A control panel supports users to indicate their tracking purposes during analysis. An interactive scene feature graph summarizes the trajectories and presents the most dominating features at different locations. And a storyboard view leverages different shot designs and to visualize different features along the camera route. We first obtain the data which simulates the earthquake evacuation events in a city of Japan. The data are grouped into two parts. Environment that is simulated by a 2D model and agents. The dynamic movements of the agents are used to construct the evacuation trajectories. We use features to indicate important attributes in the data such as speed and velocity derivation. We also define a series of events in the earthquake evacuation analysis such as turn back, conjunction, and trump, etc. The first step is to attain the user's tracking purposes. First, users can click an area of interest on the map to indicate the tracking purposes. Trajectories relevant to this area are extracted and the underlying features are pre-calculated. Then, those trajectories are clustered to generate a scene feature graph. We obtain the most dominating feature for each cluster and use it to represent the event for the group. Different events are represented by different icons. The second step is to generate the storyboard. As you can see, the input is the feature graph from the last step. Users can indicate the preferred features or regions, and the module will generate the optimal camera path. Actually, there are two ways for the users to indicate their purposes. First is to indicate the preferred feature, and the system will calculate a path with the largest cumulative value for the feature. Second, users can select areas of interest, and the system will calculate a path that passes through this area. The associated events along the path is then the storyboard. The third step is to design different shots and deliver different events. We borrow shot design in filmmaking to achieve a comparing and intuitive understanding. For example, normal shot tracks the objects from the side. Dolly shot moves the camera towards or away from a subject while filming, and the spring screen divides the screen and shows several images simultaneously. Here is the short video description of our system.
Comprises of three parts. The first is a control panel, which supports users to indicate their tracking intention in earthquake evacuation analysis. The second is an interactive scene feature graph, which summarizes the trajectories and presents the most dominating feature events at different locations. The green path is the optimal camera route, which is automatically generated based on user-specified features or regions. The third is a storyboard view, which leverages different shot types and compositions to visualize different feature events along the camera route.
use one case to show the efficacy of our system. The case is to exploring evacuation by using shot designs. The experts obtain a trajectory overview and want to explore an area of interest. The system generates a feature graph from the trajectories in this area. The experts find that agents in this central area had to pass through some building-intensive areas to reach the shelter in the west, so the experts send 10 back as the preferred features. Then the system automatically generates the optimal path as indicated by the green color. Our system starts with a panorama shot to check the evacuation group. Then, the camera started checking the group with a normal shot. They observed that the agents turned back and select another evacuation route because the buildings along the way were cramped and all the roads were blocked. The system detected this event and reduced the camera movement speed. That allows users to observe the situation. After the turn back event, the agents find a way to reach the shelter, and the camera continued to check the group using the normal shot and then the dolly shot. In another case, agents may arrive at a low intersection, and some of them may rush to the shelter in the one corner while others run to another shelter. Our system automatically splits the screen to simultaneously check these two groups. Here is the video description of the case. For other cases, please refer to our paper.
Case shows how the earthquake researcher obtained a comprehensive picture of the evacuation process. E1 first obtained an overview of the trajectory distribution in the urban environment and specified the area of interest. CVIS automatically computed the scene feature graph of the trajectories from the central areas to the shelter in the west. E1 was quite interested in turn-back events and set it as his preferred feature. The group with the maximum turn-back value was selected, and the optimal path was automatically generated. The green path is the optimal camera route. After obtaining the camera route, shot types of the key locations along the route were determined. The tracking began with a panorama shot that shifted the view from the global map to the target group. At the end of this panorama shot, the camera started tracking the group. The group was passing through narrow roads between buildings, and the camera switches to a normal shot to present the evacuation. E1 observed that the agents turned back and selected another evacuation route. Our shot composition algorithm switched to dolly shot when detecting a turn-back event. The agents finally found a way to reach the shelter, and we used the normal shot to track this group until they reached their destination. We continued filming the situation around the shelter by using the dolly shot. We employ the split-screen technique in multiple cameras to present a comprehensive picture of the evacuation. Upon arriving at the road intersection, some evacuees rushed to the shelter in the upper left corner, while some fled to the shelter in the bottom right. We switched to the split-screen shot type to simultaneously track these two groups until they reached the shelters.
To conclude our work, we propose a shot design approach to tracking evacuation behaviors in earthquake evacuation. To be specific, we built a scene feature graph that identifies the most dominating evacuation events and calculates the optimal camera route based on user-specific regions or features. We also leverage different shot designs to represent different events along the path. In the future, we will apply our method to examine various uncertainties involved in the multi-agent simulation to obtain more interesting results, and also show major events which can be outside of the selected group. Regarding the camera shot designs, we will extend to a formal and comprehensive design study. Thanks for your attention, and I'd like to take any questions.
Thank you very much for the video and interesting insights here. While everyone is thinking of a question, I will start with my own. So the data that you use is simulated data, right? So
Yes.
the simulation of the traffic and in a certain situation of an earthquake.
Yes.
How do you or is the incidents that you simulate there? So, for example, roadblocks or the point where people have to turn around. Is that something that comes from the domain experts where they say, okay, if there is an earthquake, we think that at this point we will probably have a problem, or is that also randomly chosen?
The data are collected from simulated experiments caused by a large earthquake. And we cooperate with Tokyo University, and they help us to run the experiments and simulate and generate the simulated data. And we use we use the existing visualizing software like Palavis or AVS to help users to understand how the how the users are. I mean, how different agents are evacuated when earthquake occurs. And so we find that they can hardly get the insight because the existing software cannot reveal the underlying features because the feature may involve or fuse, and they can change along with the time. So we develop our visualization software and and to extract the major events at different locations and time steps, and then we leverage different camera shot designs. So in the beginning, we may use a parallel shot, and with something abnormalous events happen, we change the camera to the dolly shot to capture more details because to review the reasons such as the road are blocked due to the corrupt buildings. So we can understand the evacuation behaviors during the large earthquake.
It's difficult to know where the earthquake will create problems in real life then, but it's in any case that helps them to understand the evacuation routes, and I guess.
Yeah.
That
So actually the data can be generated by multiple simulations. So the visualization can help the expert understand where the simulation is correct or not, because they may change the parameter of the model, and they get the simulation results, and they use our system to see the visual results. Right.
So one of the contributions in the papers is the camera positioning, and but this is also not tied to the emergency use case, right? You could this is independent from emergency management. I mean, you could apply this to many other domains where you have geographical data and camera movement.
Yeah, the reason we leverage the filmmaking techniques followed is that the screen is very limited. We should emphasize the major events, but different events may require different cameras. It's just like when we watching a film, they use different short times to convey different feelings and use this to connect with the audience. So we use this kind of storytelling techniques to convey our insights to the users, because our target users may from different domains, like the experts in earthquake. They may care something about how the model, what's the results of their model. And some users may from the ordinary people. They care about how to evacuate from their home to the shelters. So our system can generate different storyboards, and the storyboards will generate views and rules according to their requirements. Like the experts may care about some features, but the reasoners or ordinary people may care about how to run to the shelter in the shortest time. So they can define their area of interest or their interested features, and our system can generate different storyboards. So, like the contribution of the paper is that how can we leverage the storytelling techniques to reveal what we find to different groups of people.
Thank you very much for this clarification also. And
yes, thank you, Professor.
And let me take the opportunity to thank all the authors at this point again for presenting their work so nicely, and for the nice and interesting Q&A session. And I hope the audience also enjoyed it. Give them an online clap if you like. It definitely was an interesting session for me. So thank you, everyone, and see you around online and virtually. Bye bye.
Thank you.
Take care. Thank you. Bye bye.